Course 1, Saxon Math Lesson 1. This year is called Adding Whole Numbers and Money, Subtracting Whole Numbers and Money, and talking about the first part of fact families. So let me fast forward through some of the power-up and mental math, problem-solving things we do in class to the lesson material for you to view here today. And if this is your first time viewing a video from my class, keep in mind you can pause, stop, replay, rewind, fast forward. Whatever it takes for you to learn this material best for you is very important. You make this video useful to you, and it's my hope that actually having a video lesson can be better than me in front of you teaching for all of those different reasons, that you can see things again, you can pause, take a break, you can think about it, see it over again, any of those things. So don't hesitate to talk to me if you have any questions. But the new concept to start, adding whole numbers and money, reminds there's a couple terms we're going to use throughout a school year that are important. Some of the first ones you want to know in math class are add-ins and sum. All right, the add-ins are the different things you are putting together in a addition problem to get to your answer, which is the sum. So this number 3 right here is an add-in. We call it an add-in, being added, right? This is another add-in, the number 5, okay? They're being added together to get a sum. Now in this case they show an equal sign and 5 plus 3. Notice 5 plus 3 different order. This means they are the same no matter what order you put add-ins together, which we call the commutative property of addition. Don't be afraid to say that out loud. Commutative property of addition, not commutative, not community, not communicative. It's commutative, and you would think names for things going on in math are not as important, but Saxon likes to ask those questions. They're good vocabulary in math. So if you would open up your math notebook, and at the top here, let me get my mouse. And at the top you would just write something like Lesson 1 or LS1 if you want to use some kind of abbreviation. And then skip a line down and start to keep track of terms. Sum was the solution or answer in an addition problem. So you could put those terms down. But the big one I really want to make sure you get is commutative property of addition. And if you don't want to write a definition, the definition being that add-ins can be rearranged in an addition problem to the same result, perhaps you just use an example to show like they had. So next to that then, you could just show 3 plus 5 is the same thing or equal to 5 plus 3 in your notes, okay? And you've got this figured out, okay? Next, let's see what we have. So add-ins, the numbers being added, can be rearranged to the same result in your addition problems. Here we have in example 1, the addition of 345 plus 67. When we add whole numbers on paper, we write the numbers, so place values. When we talk about place value, we're talking about location of the numbers on here. 5 being further to the right means it's not worth as much as the next over. 4, which really is worth 40, because it's in the tens place, and 4 times 10 is 40. That's why we say 345. 5 just being worth 5, and then what do you think 3 is worth, really? It's worth 300 in the hundreds place there. So really, in expanded form, we've got this number. And we want our group of 5s to be getting added to the other groups of 1s, which is the 7 and the 67, and the 40s to be getting added to the 60s, because they're alike. Okay, so that's why we line all of this up so that it's same place values. Ones, tens, hundreds. Okay? Ones, tens, hundreds. So you add 5 and 7 to get 12. And of course, if you have a double-digit sum there, you need to put the 1 of the 12 above the next column, which is now in the tens place, making sense because the 1 was the tens place of the 12. And you put it in this column with 4 and 6. 10 plus 1 is 11. Put your 1 up here from the 11. And 3 plus 1 is 4, your final sum being 412. And you can check that in your calculator now that the book got it right. We added the digits by column, which is ups and downs. 2 add-ins get us to the sum. How can we check? Well, according to the commutative property of addition, you can rearrange this and you'll get the same result. So they put the 67 on top. Now just be careful that you don't write the 6 over here and whatever it is, I don't know, you'd end up with maybe a 0. That's the problem. You'd end up with a 5 over here. It would not come to the right result. So it's very important that you're lining up your place values. Okay, so 7 and 5 get lined up, and you end up with this space right here. And that's okay. All right, so you can rearrange it either way, and that's great if you prefer 7 on top of 5. If it's easier in your head, you add it that way. Whatever works well for you. Commutative property, add-ins and sums, adding numerals and also adding money, right? Here we have an example to $1.25 added to $12.50 and then a cool even $5 bill there all put together. So you wouldn't, unless you're putting it in a calculator, leave it in this horizontal form. Instead, we want to make it vertical. A good word. And now, what are we lining up? When we add money, we're writing so that decimal points are aligned. In a line is what aligned means. So check our dot is right above, just like that. And then you check, okay, 1.25 is the way that's written. 12.50, and see how that's naturally going to put all the place values just how they belong. 5 needs to get written with extra zeros because 5 without anything, it's actually $5 and no cents. So you have to write it here with 2 zeros. Adding it together, check it with your calculator, $18.75. One more to add to our notes. A property of addition is called the identity property of addition. And the identity property of addition in your notes is quite simply that if you add 0 to anything, it doesn't change the sum. So you could write in your notes, instead of all those words, just 5 plus 0 being the big numeral, or the big whole number there, equals the same number. Okay, if you can remember what that means, that's all you need for the identity property of addition. Okay. We subtract one number from another number to find what's called the difference. All right, and I like how in this book, this new book, they automatically introduce what the names for the numbers going into a subtraction problem are called. Maybe you've never known, but they are called the subtrahend. And let me double check, is that the first number being listed in a subtraction problem? Nope. So let's start with minuend. Minuend is number on top in a subtraction problem. Meaning it's the number probably supposed to be bigger that you can take from. I'll add that, take from. And the subtrahend is on bottom in subtraction. I guess take away, if that makes sense, however you want to write that. And difference, what was difference? It's like the sum, but to a subtraction problem. The answer to a subtraction problem, okay? And however you want to do that in your notes, if you want to show any more of anything, you could show, right, 5, and then maybe color code, minuend is red. Subtrahend is what you're taking away, 2. And if it's subtraction, we set it up this way. We want the big number on top and find the difference. Difference between 5 and 2 being 3. All right, good terms. Subtrahend, minuend. Well, they use the same example. Does the commutative property work for subtraction? Think about that. 5 minus 3 equals 2. Can we rearrange subtrahend and minuend to find the same difference? No, you would not be able to do that. In subtraction, if I move the 67 up here and take away the 345, I get what's called a negative integer, and we'll get to that another time. So not commutative. There is no commutative property of subtraction. So subtracting 345 and 67, you get what we call borrowing, and it's easier early on, but eventually borrowing can get tricky when you get things like fractions and decimal numbers. So remember, we set up so that ones are lined up, tens are lined up, and if it helps you, you can put a 0 here because there are no hundreds in 67. And we find our difference. What's the problem here right off the bat? Well, the 5 is smaller than the 7. We want to take 7 away from 5. Imagine you have 5 cows and your neighbor asks for 7. You're not going to be able to give him 2. We have a problem, so you have to lend him 2. We're going to borrow. He has to lend, or he has to wait for 2, I guess is how I should say that. So we're going to actually borrow 10 from here so that it's only worth 13. And this is going to be 15. Or 30. We're borrowing 10 from here, so it goes from 40 to 30. And we add the 10 we took and give it to the 15 to make it 5 to make it 15 is what we're doing. So 15 minus 7 is 8. 30 minus 60 we can't do, so we have to take away from here. Now we have 23 minus 6 is 17. How did I do? I did not do well. I made a mistake. What did I do wrong? I added the top there. I shouldn't have done that up here. So when I have this and I take my 2 away, this is just a 13, not a 23, right? And then 2. So when I borrow from here, I'm borrowing a 1 each time. 278. Okay? Now, with dollars and cents, you do the same thing. You line up your decimal. So they have $5 and they need to pay $1.25 away from it. You need to borrow 1 from the tens, but they have none on the tens, so we borrow 1 from the hundreds place. We move and make this 9 because we're going to take away 1 and put it here. 1 minus 5, really this is 10 minus 5 is 5. 1 and 0. You could write this as you could write your 1 next to the 0 to remember that this is really 10 minus 5 is 5. And we had 9 left here because we had taken 1 from here, but we also took our 1 from here. So 9 minus 2 is 7, and there were 4 left here. And if we had to borrow again here, that would mean we would have the smaller number on top, and these would have to get switched around. So you should never end up with running out of numbers to borrow from. Just about finished. You can check the answer to a subtraction problem by actually adding. If you take the difference, 375, plus the subtrahend here, $1.25, it should come to your original total, right? And that makes sense. How much change you got back plus how much you paid should give you what was in your wallet in the first place. Now, fact families. Couple things to think about: inverse operations, where we can undo an addition by subtracting one addend from the sum. The three numbers that form an addition fact also form a subtraction fact. For example, 4 plus 5 is 9. You can say 9 minus 5 is 4. The numbers 4, 5, and 9 are a fact family, rearranging to form different facts. So the addition and subtraction fact families are the simplest. You could really use any three numbers that come to a sum. And if it helps, you can think of these as triangles. Okay, so the one we just did, I think, was, what was it? 9, 5, and 4. Maybe put your big number up here. 5 and 4, and you have a fact family to show is an addition subtraction fact family where 5 plus 4 is 9, and you can arrange that to be according to the commutative property. 4 plus 5 is 9, or start to do subtraction. Not 5 minus 4 because that's going to give us 1, but 9 minus 4 is 5, and finally 9 minus 5 difference is 4, where we create 4 different addition subtraction problems from the triangle fact family here. You do it with 11 plus 14 is 25, like this. You can follow along in your book. That's page 10, right there. And finally, example 6 is 11, 6, and 5. You can rearrange subtrahend and difference. You can also take your original number in the subtraction problem and make it a sum and an addition of 5 and 6. All right, why don't you attempt pick an addition, A or B, one from here. Pick a subtraction, C or D, one from here. Do E and do F. So 4 total of the lesson practice. In your math notes, please. So if you're following like on mine, you would start writing down here then A or B you would do, C or D you would do, E, and I think it was F. And you will show me those when I get a chance. I'll come back around to you somewhere during algebra class. Thank you.